Since the dawn of aviation, planes were engineered to dominate the skies. But in the 1960s, Russian engineers prototyped an unconventional aircraft named the Ekranoplan that flew at only 5 to 10 meters above sea level. It was also the world's largest and heaviest plane at the time, sitting at a length of over 92 meters. Now, although the Ekranoplan sounds like an incredibly impractical design, its low altitude actually provides for a surprising amount of speed and efficiency for its weight. This was due to a phenomenon known as the ground effect, which allowed the Ekranoplan to fly at speeds that most other planes its size would struggle to maintain. Let's take a deeper look. The ground effect describes the reduced aerodynamic drag generated by an aircraft's wings when they are close to a fixed surface, such as solid earth or water. But in order to understand the ground effect, we first need to learn about induced drag, which is the aerodynamic drag that is created when an aircraft is generating lift. To visualize why induced drag happens, let's take a look at a cross-section of an aircraft's wings, also known as an airfoil. Due to the curved shape of the airfoil, the split airflow will travel faster on top of the wing compared to below the wing. Bernoulli's principle states that the faster the air travels, the less pressure it will exert on the wings. As a result, this will create a pressure imbalance, where the air pressure is higher below the wing than above it. High pressure air really wants to move towards low pressure air. However, in this case, the wing is in the way, except at the wingtips, and that's why the high-pressured air will spill around the wingtips, creating a downward and outward flow of air known as wingtip vortices. These rotating wingtip vortices deflect the air coming at them in a downwards direction. This is known as downwash. Okay, that was a lot, but how does all of this connect back to induced drag and the ground effect? To help you make this connection, let's break down the direction of lift into its vertical and horizontal vector components. Since the direction of lift is always perpendicular to the airflow coming towards it, when that airflow is deflected downward by wingtip vortices, you will get a rearward inclination of the direction of lift. Notice that the horizontal component increased as wingtip vortices formed. This horizontal component is induced drag. Now let's imagine the same scenario, except this time the aircraft is near the ground, either during landing or takeoff. Well, downwash, which causes induced drag, requires that the airflow be deflected downwards unobstructed. But when the aircraft is flying close to the ground, downwash can't be fully formed, because, well, the ground is in the way. In other words, there's not enough space for wingtip vortices and downwash to fully form, because the ground is obstructing the airflow. So now you know why Ekranoplans fly so close to the ground. Because they're always experiencing the ground effect, they face less induced drag compared to other planes of its weight class, and are thus more efficient. Now, even though this video is coming to an end, I hope that the innovative and experimental spirit of the Ekranoplan will inspire you to continue exploring the vast and beautiful world of physics. Thanks for watching, and goodbye.